Well, I'm a bit, I don't know, my friends tease me that I'm a bit philosophical, but I'm sort of intimidated talking to actual philosophers, so hopefully this will be okay. The subject that I'll talk about in this context is the subject of singularities and cosmic censorship in general relativity. Well, let me give an outline of what I'm going to say. So I'm going to begin with a brief discussion of general relativity from the point of view of the Cauchy problem, because this is somehow fundamental for being able to formulate the types of questions that I would like to formulate. This being done, I will then talk about the Schwarzschild solution, very familiar to most of the audience here, and Penrose's incompleteness theorem, and somehow use the situation that comes out from understanding those two things to motivate what are the cosmic censorship conjectures. I will formulate them, say a few words of why we hope that they're true at this point. And then next time, tomorrow, I will talk more precisely on what is the status of these conjectures, what partial results are known, and where does that leave us? What are the prospects for a complete resolution? So this is the outline of my talks. So let's begin with general relativity as a Cauchy problem. So when Einstein originally arrived at the definitive form of his equations in November 1915, equations that we all know and love written here, then their character as partial differential equations was still poorly understood. Of course, when you write them like this, it's not even clear that they are partial differential equations until you remember the definition of the Ricci curvature in terms of an explicit expression of up to second derivatives of the metric potentials. One of the great, if you want, conceptual advances in the subject was that even in the absence of matter, so even when you set the energy momentum tensor to zero, the resulting system of equations, which of course simplifies, as you all know, to the statement that the Ricci curvature is zero, these equations are in fact hyperbolic, they are wave-like, and they have a well-posed Cauchy problem. That's to say, you can talk about dynamics. And this is even, you could say, somewhat ironic, because of course the form of the Einstein equations was governed by, in some sense, properties of the right-hand side, in particular the sort of requirement that whatever the right-hand side is, it should be divergence-free. And in some sense, inspired by whatever you want to call them, Machian tendencies, Einstein really thought of the right-hand side as determining, in some sense of that word, the left-hand side, at least at some stages of the process that led to these equations. So the fact that the vacuum has a world of its own was something which, in some sense, was completely foreign to the procedure that brought general relativity into existence. But nonetheless, this is a fact. So let me say a few more words at the, let's say, conceptual level about the Cauchy problem, because I think that somehow how important, subtle, and even, you could say, unexpected an achievement this was is not so well known. So understanding that, yes, the Cauchy problem makes sense in general relativity required understanding a whole host of conceptual issues. So the first issue is, well, you have a Cauchy problem, an initial value problem, then you have to talk about initial data. So what constitutes, in general relativity, initial data? What constrains initial data, and do there even exist sets of initial data? So in some sense, actually, this problem began with Hilbert, who was the first to write about the Cauchy problem in his, I guess it was 1918, manuscript on the foundations of physics. But he actually, in some sense, ignored this problem, or perhaps didn't realize it existed. That's to say, he successfully solved a set of equations without imposing constraints. So he was, without knowing it, not actually solving the Einstein equations. So the first people to really identify, the first person to really identify what these constraint equations are in the language of classical differential geometry is Dafermos. And these equations were sort of studied further by his student Lichnerowitz, and subsequently sort of there's been a huge literature on the constraint equations, plays an important part of mathematics. Important triumphs of mathematics in that regard are, sort of, for instance, the positive mass theorem, which is a statement about the solutions of the constraint equations, if you will. So this is one conceptual issue, that sort of zeroth, if you want, conceptual issue that has to be understood. The next conceptual issue is, in what sense are the equations hyperbolic? So again, you could say that this started with Hilbert, who was the first to talk about the Cauchy problem, but actually he talked about the Cauchy problem in the realm of analyticity, where you don't need any sort of hyperbolicity in order to talk about sort of solving the initial value problem. But of course, it's well known through work of beginning with Hadamard that in order for the Cauchy problem to really make sense, then your equations better be hyperbolic. So in what sense are the Einstein equations hyperbolic? Well, somehow Einstein was the first to stumble on this, in that he was the first to predict gravitational waves. And gravitational waves, in his prediction, is basically the statement that, well, if you linearize the Einstein equations at least around the trivial solution, then you get the wave equation. So in that sense, he stumbled already on the hyperbolicity, but like with other things, he sort of took that prediction back at various points, etc., etc. But in the meantime, this idea was taken up by de Donder, who first talked about what we call the harmonic gauge. In some sense, the linearized setting goes back to Einstein. And then finally, Dafermos. So this was a big achievement. So indeed, the equations are in some sense hyperbolic. We have some sense of what we mean by initial data, but that doesn't mean that you can solve them. That does not mean that you can solve the initial value problem even locally. Because at the time that all this was done, these equations were just too nonlinear to even be able to talk about dynamics. So, of course, we all know in the world of ordinary differential equations that for ordinary differential equations, it's a very general theorem. You give me initial data, there is a unique solution. Okay, this is well known. And you can prove this theorem irrespectively of the extent to which you can understand what is the global dynamics of this unique solution. So somehow the notion of dynamics makes sense, but to understand the particular dynamics, you have to work. Right? But when general relativity was formulated, one was not at all at this place yet for the Einstein equations, or indeed for any nonlinear hyperbolic equations of mathematical physics. So, for instance, compressible Euler equations of fluid mechanics. One did not know how to talk about dynamics for these equations because they were very nonlinear, and one did not know the quantities that controlled in any sense of the word dynamics. So this was one of the great accomplishments of the theory of partial differential equations from the first half of the 20th century, and some of the people involved are written here, where it was understood that a generalized higher order notion of energy was sufficient to understand that, yes, somehow locally at least, you can talk about well-posedness of nonlinear hyperbolic equations of this type, okay, including the Einstein equations. So this is a very important conceptual advance somehow, that there was this hidden structure behind the Einstein equations that allows you to talk about dynamics. But there's still some more features that are particularly very important for the purpose of general relativity. So one is, what is the geometric property of spacetime that ensures uniqueness in the large. Because you see, we all know from the wave equation that sort of what gives you uniqueness is actually something more general. It gives you more than just uniqueness. We have something called the domain of dependence theorem. So finite speed of propagation. So what is the analog of the property that sort of tells you that this type of argument still allows you to show uniqueness for the Cauchy problem, in the geometric setting of general relativity, but on manifolds? So this is the notion of global hyperbolicity, and this notion was identified by Jean Leray. Okay, and it's his famous notes published, I guess, in 49 in Institute of Advanced Study. And the final conceptual issue that had to be understood was, well, maybe I'll return to ODEs in order to say this better. So, as I said, in ODEs, there's a very general theorem that we can say, which is you give me initial data for an ODE, there exists a solution. But we don't just say that there exists locally a solution. We can say that there exists a maximal solution. There exists a maximal time interval on which you have a solution. Now, that time interval could be infinity, in which case we say the solution is global. It could be finite. And in fact, in the ODE case, you can give a characterization of if it's finite, sort of the trajectory of the solution has to leave all sort of compact sets. Okay? But in any case, you can talk about the maximal solution. You can talk about the solution of the initial value problem. So, general relativity, this was a conceptual problem, exactly because the spacetime manifold on which the solution is supposed to live is not given a priori. It's part of the solution. And if you have two solutions, it's not immediate how to compare them because they don't a priori live on the same ambient space. So sort of going from the existence of a sort of local solution to the existence of a maximal solution, which in ODEs is a triviality, in general relativity wasn't. And this was really only resolved quite late in paper of Shukibra and Gerosh. And in any case, to make a long story short, this is, if you want, the fundamental theorem of general relativity, which sort of summarizes all the contributions of the previous slide, that says that, well, given a smooth vacuum initial data set, and I say smooth for convenience because hidden behind all these statements is something much more quantitative. There exists a unique smooth spacetime which solves the Einstein vacuum equations, which is Ricci flat, which admits the initial data as a Cauchy surface. Okay? And this notion of Cauchy surface is exactly sort of the statement that the spacetime has a Cauchy surface is the definition of global hyperbolicity. So this is fundamental for uniqueness. We'll see this later on. And finally is maximal. That's to say every other smooth spacetime with properties 1 and 2 isometrically embeds into this one. This is maximal. And, well, similar theorems can be proven for suitable coupled Einstein-Mader systems, of course, provided in particular that you know how to prove it for the Mader system alone. So this is the fundamental theorem. Now, I just want to make one comment that, which is sort of topical in view of the nature of this mini-series and some of the previous talks, that what allows you to prove a local existence theorem is very quantitative. It is quantitative control on the solutions. But there was something very annoying about the way this theorem was proven, this maximal theorem. And the very annoying fact was that the traditional proof of this theorem appealed to Zorn's lemma. So this theorem was mysteriously non-constructive in a way that is very inappropriate in mathematical physics. So I'm pleased to announce that one of my students, Jan Zbierski, has successfully completed the de-Zornification of this result. So this is a completely constructive statement in mathematical physics. Okay, so this is the fundamental theorem of general relativity, and this unique object, maybe I should say, is called the maximal Cauchy development of initial data. Okay? And somehow, without referring to sort of the framework of this fundamental theorem, it's very difficult to understand any issue corresponding to singularity. So let me give these remarks or meta remarks in the sense that they sort of apply not just in the context of general relativity, but in the context of other theories of classical physics governed by PDE. So the above theorem says that we can talk about dynamics. Okay? In principle, one can talk about dynamics in general relativity. That's what it says. Dynamics is a well-defined notion. And given that, it's now possible to rationally entertain whether a certain property of a solution of the Einstein equations is stable, in the sense that this property persists to perturbation of initial data, or whether a certain property is generic, all right, in the sense that this property holds for all solutions arising from an open and dense set in the moduli space of initial data. Okay? Now, of course, these notions of open and dense set in the moduli space, yes, they require some sort of measure, but typically with these problems, that notion is not problematic, actually. Okay? So the problem is actually typically not there. So I should give a huge caveat, particularly given the subject of this conference, that there are settings where the above notions, as I've discussed them, are not necessarily relevant. And in particular, in general, when solving backwards in time, very often knowledge of initial data is secretly correlated with a particular property of past evolution. So these questions are not necessarily so natural to ask. And one instance of this is in the context of cosmology. So in this talk, I will actually focus on future evolution of isolated self-gravitating systems where such caveats do not apply and where such questions are, in some sense, clearly the correct question. Okay. So with these remarks given, let me go to the notion of isolated self-gravitating systems. There was an introduction of sorts to this notion, although I can't really use that introduction for obvious reasons. So, well, first of all, for pedagogical clarity, I'm going to restrict consideration to vacuum equations. Okay, so I'm only going to talk about vacuum. This is not because in the real world there is vacuum. This is not because this is simply for pedagogical clarity of this talk. Okay? So in this context, the mathematical idealization of the notion of the initial state of an isolated gravitational system is given by what's known as an asymptotically flat data set for the Einstein equations. So what does asymptotically flat mean? It means that if you throw away a big enough compact set in sigma, the initial 3 manifold, all right, then the rest is diffeomorphic to R3 minus a ball. Okay? And moreover, with respect to the ambient coordinates of R3 that you get by this diffeomorphism, the metric and the second fundamental form approach the Euclidean metric and 0 as x goes to infinity at suitable rates. So this is somehow the notion. So important to understand the sort of what is being represented. So faraway observers who are not part of the system, let's say us, all right, we have to be understood as belonging to an asymptotic boundary of spacetime at infinity. Okay? To use the terminology of George Ellis, this is not a real infinity, but it's a useful one, and for this reason I'm not going to discard it. I'm not going to replace it by a very large number. This would mathematically be suicide. We would not be able to formulate much. But it is, of course, and I resonate with what George Ellis said in the following sense, that as an analyst, the type of things that we do at the end of the day are quantitative, And one should always, a posteriori, look back and try to understand quantitatively what some of these statements actually mean. Typically, and maybe I'll return to this comment, the sort of behind qualitative statements that I will present, there is something much more quantitative that does not follow from the qualitative statement. It's what is actually proven. But it's much harder to transmit. So there is certainly something which is very appealing about this picture conceptually, and it's very difficult to imagine any of these issues sort of having even been identified without the crutch given by this limit. Okay. So this is the notion of asymptotic flatness. Let's go on to the Schwarzschild solution and discussion of Penrose's incompleteness theorem. And this, as I advertised, will lead us subsequently to a discussion of the cosmic censorship conjectures. So the Schwarzschild metric, well, familiar to almost everyone in this room, I'm sure. The first non-trivial explicit solution of the Einstein vacuum equations to be discovered, already published in January 1916. So in local coordinates, you can most succinctly express the metric element in the form which is written here, and it's well known to everyone here, where m is a real parameter. But there was a lot of confusion which was caused as to what ambient manifold m, the above metric expression, should live on. Now, often it's said that people did not understand the difference between coordinate singularities and real singularities, and somehow this awful language is used to discuss this issue. But I think it does not do justice to what people were doing, and it's clear that people understood what a coordinate singularity is. In fact, no one was ever confused about the coordinate singularity of the spherical metric, for instance. But this question of where this metric should live on, it requires a choice. You have to choose where you think it should live on somehow. And it was not clear in what sense the theory told you where it had to live on. At least the theory as the theory was understood initially. So somehow one should not be dismissive of somehow early attempts to try to understand the Schwarzschild solution. In any case, in some sense, what does or can tell you what manifold you should call the Schwarzschild solution is precisely the problem of dynamics. Because in some sense, in the problem of dynamics, as we saw, you just tell me the initial data, and dynamics unambiguously tells you what is the Cauchy evolution of that data. Okay? So from this point of view, it makes sense to consider Schwarzschild, what you call Schwarzschild, as the maximal future Cauchy development of appropriate spherically symmetric asymptotically flat initial data. And that's depicted here, and I'll return to these depictions. Of course, they're quite familiar to most people here. However, in order to do this, you have to generalize the notion of asymptotic flatness that I gave you, because somehow, except in the, let's say, trivial case of Minkowski space, thought of as a special member of the Schwarzschild family, Schwarzschild solution does not admit, finally, an asymptotically flat initial data set in the sense that I defined. Okay? It admits an asymptotically flat data set with two ends. That means that in this definition that I gave you, you have to allow that if you throw away a compact set, then you have not one, but the disjoint union of, let's say, two, in this case, regions of this type. So, well, first of all, I motivated asymptotic flatness as an idealization of the notion of an isolated gravitational system. And this is, if you want, how one motivates this notion of having this end. There is no sense in which having two asymptotically flat ends is of any physical relevance, at least in the sort of in the classical astrophysical domain of general relativity. Nonetheless, we always look at this picture. So why should you even consider this from this point of view? Well, the short answer is as a proxy for something else, which is just a little bit harder to talk about. So if we go beyond vacuum for a minute, So if we consider the maximal Cauchy development of an initially homogeneous dust ball, which is homogeneous and spherically symmetric in a ball, okay, surrounded by spherical symmetric vacuum. So we look at this. And as I said, we look at its maximal Cauchy development. That's to say, we look at the solution of the, in this case, coupled Einstein dust system. So Einstein-Euler with pressureless fluid. Then one obtains a spacetime, which is the celebrated Oppenheimer-Snyder spacetime. So I've depicted this spacetime here for those of you who can read these pictures. And this spacetime coincides with Schwarzschild outside the support of the matter. Okay. And in some sense, this is actually the type of spacetime that one would want to talk about in the context of the problems that I'll discuss. But it will be pedagogically useful, if you want, for me to treat the two-ended Schwarzschild as a proxy for this spacetime. And the various reasons that I will do this. One of them being that, for now at least, I really just want to talk about vacuum, and I want to have the crutch of an explicit solution that you can talk about, that it's easy to compute, etc. Okay? So you have to trust me that sort of this usage of Schwarzschild as a proxy is honest, okay? And I will continue the talk as if sort of the notion of two-ended asymptotically flat data is reasonable, physically admissible, etc. Okay? But if you're worried about that, secretly you should know that there is something else behind it, but it's more complicated to talk about, and I don't want to at this point. Okay, so now that we said that, let's return to Schwarzschild. Now that we've sort of made ourselves comfortable with Schwarzschild, so now from the point of view of now, the maximal Cauchy development of sort of this two-ended asymptotically flat data, this is perfectly reasonable data, physically admissible data. Schwarzschild is its maximal development. And lo and behold, we see the following, that this maximal Cauchy development, it turns out to be future causally geodesically incomplete. So that's to say that there exist observers, like observer gamma, which is depicted above, who live for only finite proper time in this maximal Cauchy development. Okay. So this is the situation in Schwarzschild, and given that the data is physically admissible, well, in view of the caveat that I told you, this is a problem, it seems. So, well, to the extent that this phenomenon was understood even, there was a sort of an obvious way to hope to get out of this problem, which is to hope that, well, okay, this Schwarzschild solution is very, very special. It's sort of initial data is admissible, but very, very special, particularly because it's spherically symmetric. So maybe this, quote, pathology was related one way or another to the high degree of symmetry of the data, and thus would go away upon perturbation. Okay? So this was, in some sense, an obvious way out to bet on when, in some sense, this type of property was first discovered. I mean, maybe I should say that this talk is unapologetically revisionist as far as the language that I use, because obviously sort of saying all these words in this language was only really done after many of these issues were understood, and this is why I'm using this language. But okay, I'm not a historian of science, or in any case, this talk is not a historical talk, so I think I'm okay with that. All right, so that was the hope, but that hope was falsified, and that hope was falsified in a most spectacular way as a sort of mere corollary of Penrose's celebrated incompleteness theorem. And the corollary, so I'll just state the corollary, says the following. For all sufficiently small perturbations of Schwarzschild initial data, then the maximal vacuum Cauchy development is still future causally geodesically incomplete. Okay. So this property, this incompleteness property, is a stable property. So it does not go away. So one interesting thing about this theorem and problematic thing about this theorem is that this theorem does, if you want, make this is a genuine contradiction argument, this theorem. So it does, there is something completely non-quantitative about this theorem. So in some sense, well, when we talk about cosmic censorship, part of cosmic censorship is correcting for precisely this. So it's really remarkable that somehow the setup allows you to state this theorem. But here it is, and it has tremendous implications for one's view of the subject. All right, so back to Schwarzschild. So, this is a stable property. So one way or another, you have to come to terms with it. And of course, there are many ways to try to come to terms with it. One is, of course, throwing away the theory, which is perfectly reasonable way to come to terms with this, if you think that's the right way. The so-called cosmic censorship conjectures, they are best viewed as another way to try to come to terms, so to speak, with Schwarzschild incompleteness. And they were originally motivated, if you will, by two, quote, good aspects, which are associated to the nature of Schwarzschild geometry, which makes its incompleteness seem more acceptable, in quotes. And I'm not going to philosophize on the meaning of either of these two words. Again, a posteriori, after one has formulated these conjectures, and actually, well, really one should wait till one has proven these conjectures, which will be a while, then maybe then is the time to philosophize on sort of what these words mean and have the conjectures captured. But in any case, let's discuss these properties and the conjectures. So as far as the first property, let me talk about null infinity and the black hole notion. So null infinity is what we have been depicting in these space-time diagrams by script I plus. And this is the asymptotic boundary at infinity that these Cauchy developments have, that you can attach. You can prove that you can attach to these Cauchy developments, which, if you want, idealize, quote, faraway observers in the wave zone. That's to say, observers who are far away and positioned such that they receive gravitational and electromagnetic radiation from, let's say, perturbations of the system. Okay. So again, in reality, this is not at infinity. It's very far away, but in this idealization, this is infinity. So the first property that we notice, well known to most of this audience, is that the past of future null infinity, what you can read off from this diagram immediately, has a non-trivial complement in the space-time, and this is exactly what defines the very notion of black hole. Okay, so it is in this sense that this maximal Cauchy development of initial data has a region which we call black hole, and of course everyone here knows what that means. That means that space-time events in this black hole region cannot send signals to faraway observers in the wave zone. Okay? In particular, it so happens that all incomplete gamma, so all curves, remember we said that Schwarzschild was future causally geodesically incomplete. That means that there exist causal geodesics gamma with a property that they only exist for finite affine parameter. Okay? So, moreover, it turns out that all such geodesics, they enter this region, never to emerge from it. And in this sense, the incompleteness, the geodesic incompleteness, is not seen by future null infinity. Okay, so to say it another way, faraway observers in the wave zone do not see. Moreover, and this fact is sometimes not said explicitly, but it's actually, in some sense, this is the most important fact. Null infinity itself is complete. That's to say, okay, even though this observer gamma only lives for finite time, observers at null infinity, so for instance, LIGO, the detectors of gravitational waves, they observe for infinite time. Okay? And here, again, the operational meaning of infinite is for as long as LIGO is funded. So this is the, yeah, that was a joke. But, so this is the notion of null infinity. All right, so what does weak cosmic censorship say then? How can we formulate it? So in some sense, this is the weakest formulation that you can give. The conjecture is the following, that this property of Schwarzschild, that's to say the property that null infinity is complete, this property is generic. Okay? That's to say, because now, and this was the whole point of dynamics, generic means that for an open and dense set of asymptotically flat initial data in the moduli space of all asymptotically flat initial data for the vacuum equations, the maximal vacuum Cauchy development has a complete null infinity. Okay? So this is the conjecture. All right. So at this point, it's not at all obvious why one should assume that this is true generically and not for all vacuum solutions. Because it is not known whether there are vacuum solutions which admit an asymptotically flat initial data set such that null infinity is not complete. So there are no counterexamples known for the sort of predicate of the statement for any admissible initial data set for the vacuum equations. Nonetheless, there are reasons to believe that this will only be true generically, and this follows from analogy with certain specific Einstein-Mather systems, and I will talk about this next time. Okay, but a priori, at least, you could conjecture this for all asymptotically flat initial data, and somehow there is not a counterexample to that statement known presently. Okay. So this is the conjecture, and this is exactly the good property of Schwarzschild that it tries to capture. Okay, so that's weak cosmic censorship. Let me continue. So there's another good property of Schwarzschild. It's simply that when you first say it, it probably doesn't sound so good. So it's the following property. So let's look again at these observers gamma with the property that they only live for finite time. Okay? So it turns out that all such observers, all observers that only live for finite time, there's a quote, a reason why they only live for finite time. And the reason is that they encounter infinite curvature. In fact, something stronger is true. They're actually ripped apart by infinite tidal forces. So they're infinitely ripped apart. Okay? Right? With the usual caveats on the interpretation of infinite in the context of the actual field. So I said that this is a good aspect. So why is this a good aspect? One can at least be satisfied that this incompleteness, it brings with it a sense of closure from the point of view of the classical theory. That's to say, okay, it's not very pleasant for the observers in question that they are ripped apart by these tidal forces. But from the bureaucratic point of view, it's very, very good because somehow everyone is accounted for by the classical theory. That's to say, the classical theory says exactly what happens to everything that is classical. Okay? Now, if at some certain time, your classical observer is completely ripped apart and becomes some sort of, I don't know, quantum mesh, then quantum theory can take care of him from there. But classical theory has given him up as a very non-classical object. So this is really, in some sense, why this is good. Now, you might think, well, how else could the maximal Cauchy development be incomplete if something like this did not happen? What else could have happened? And when I show you this, maybe it will make it more clear why this is to be considered good. You don't have to look very far. You just have to perturb Schwarzschild ever so slightly. So everyone here probably knows that actually the Schwarzschild family is a one-parameter subfamily of a larger two-parameter family of solutions known as the Kerr family. And you can think of Kerr initial data for very small a as an arbitrarily small perturbation of Schwarzschild data, in fact. Okay? So these are really, in any open set in the moduli space of the initial data that led to Schwarzschild, you will have these guys. Okay? So what's the situation here? Well, here, this I've depicted, for those of you who can read these diagrams, I've depicted the maximal Cauchy development of Kerr initial data. And what happens is that this manifold, the maximal development, is actually smoothly extendable to a larger manifold, this sort of lighter shaded region, such that all incomplete geodesics in the original manifold, they can safely pass into the larger manifold. Okay? So in particular, they are certainly not destroyed before they pass into this larger manifold. Okay? If you could extend the maximal extension, how could it have been maximal? If you could extend the maximal development, how could it have been maximal? Well, remember that when I stated the fundamental theorem of general relativity, then to call something a development of initial data, it has to be globally hyperbolic. This notion, very important notion due to Jean Leray. So an equivalent formulation of global hyperbolicity is that all inextendable causal curves, they intersect the initial data surface precisely once. So it's very easy to convince yourself that these type of extensions fail to be globally hyperbolic. What does that mean? That means that initial data does not determine the solution. You can extend solving the Einstein equation, but these extensions are non-unique. So they are no longer determined by initial data. Nonetheless, nothing has blown up, no one has been destroyed. Everything at first sight should be completely classical. So somehow, if you want, this is a breakdown of determinism. Okay? You cannot predict the future of gamma, but there is a priori no reason why, certainly not under local considerations, why you cannot. So this is the most spectacular type of breakdown of global hyperbolicity. So, and this will be my last slide. The strong cosmic censorship tries to rehabilitate this very good behavior of Schwarzschild from this point of view that is suddenly lost in Kerr. So the statement is that for generic asymptotically flat vacuum initial data, then the maximal Cauchy development, like Schwarzschild and unlike Kerr, is future inextendable as a suitably regular Lorentzian manifold. And you should think that the manifold being inextendable is related to the notion of observers sort of who go to what you think is the boundary of the manifold being destroyed. Okay? But this is actually a cleaner formulation, so we'll formulate it in terms of the manifold itself being inextendable. So you should really think of this, as I said, as a conjecture of global uniqueness. Okay? So, of course, as opposed to weak cosmic censorship, here it is clear a priori why the assumption of genericity is required, because Kerr is sitting there as a particular solution allowed here, and this predicate most certainly fails in a very spectacular way in Kerr. Spectacular because, in fact, all observers who are incomplete can pass into an extension. So it's clear why you certainly have to put in generic. What's not clear at all is why, at this point, you should ever conjecture this. After all, in the family of special explicit solutions of the Einstein equations that you can write down, so in some sense, the most general asymptotically flat such family is the Kerr family, then the Schwarzschild case is non-generic. That's to say, if you restrict consideration to this, the only one-dimensional sort of subset of moduli space that you have a priori, then it would look like it's precisely the opposite. That you should conjecture that this is the generic situation and that this is the non-generic. But nonetheless, there are reasons why we do conjecture this. There are reasons that one can hope that this is true, and I'll discuss those reasons next time. Thanks.